This is a video to show you the relationship between the electric field and potential. Alright, and even though we've talked about it in terms of the math, the fact that there's a derivative integral relationship between the two, I want to show you what that means graphically, and that's the point of this video. So let's start with two planes, a plane that's positive and a plane that's negative, like this one here. And consider that the electric field is going to be directed from the positive plane to the negative plane, as such. And of course it's uniform, as we know for planes, that's the case. And one of the points I made is that what we're interested in is the potential difference between these two planes. In other words, the potential of the positive plane minus the potential of the negative plane is what is meant by the potential difference. Now, one of the things we do here is we make an assumption and just say, okay, we're going to, not even an assumption, a statement, and we define the negative plane to be 0. So I'll put a little ground symbol there. That's what is meant by ground. And this means that the negative plane has a value of 0, which means that the potential difference is just equal to the potential of the positive plane. Now, if we know the electric field strength between the planes, which we do because we know how to calculate it, of course. I won't do that now because I didn't assign values for sigma. But if we knew that, then we know that the relationship between the potential difference and the electric field is that the potential difference is equal to the electric field times the distance for a uniform electric field. It's not quite so clean. For a non-uniform electric field, you have to use an integral, and you have different equations if it's a point source. For a uniform electric field, this is the case. All right, so that means then that we know what the potential difference is between this plate and that plate, and we can say that V plus, which is equal to delta V, is equal to the electric field strength times the distance between the plates, where D is this. All right? But what's also interesting is that we know that anywhere in between the plates, the potential has to get from 0 to whatever it is over here. Between the plates, it has to do so as well. So if I wanted to know, for instance, the potential at this point, at this green line there, or anywhere along it, at any point along this green line, I would take the distance from that point to the negatively charged plate. That's my other distance. I'll call that D1. And the potential at that point, I'll call that V1, if you like, rather than V plus. It's the potential even in space here. There's a value for the potential. We just don't necessarily, it's a little harder to measure, but it exists. The potential exists there. It's going to be equal to the same electric field, because the electric field is uniform, has the same value throughout the space between the plates, times the distance D1. That's what the potential at point 1 is going to be. And you can say that at any point in between here. All right, so if I could draw these lines of constant potential, they'd look like this. I'll draw them in blue. They would be perpendicular to the electric field. An electric field, of course, does that. And of course, the plates themselves are also lines of constant potential. But the value of the potential at each of these points, V1, V2, V3, V plus, is going to be equal to E times the corresponding distance of that potential line from the negative plate. Okay, D, if you want to say this is D1, D2, D3, etc. Simply that product. You just have to know what the distance is, and you have to know the electric field strength. which is going to be the same at any point in between here. The electric field will stay the same, but the potential will be different at these different points. Potential will be the same, though, along these lines. That's by definition. They are equipotential lines. By definition, the potential is the same along them. Now this is true for two parallel plates in terms of what the structure is going to look like, but the same holds true in sort of in reverse. If you knew the potential field, let's say the potential field looks something like this. It doesn't have to be uniform. It's always going to be perpendicular to the electric field lines. But if you knew that the lines of constant potential look like this, remember they're like topo map lines. So these are two different constant potential lines, and I'll draw a third one in here, a different color. And I know what let's say I know what the value of these are. I'll call this one V2. I'll call this one V3. I'll call this one V2. I'll call this one V1. The electric field is the integral of the potential. I'm sorry, I didn't mean to say that. Let me reverse that. The potential is the integral of the electric field, as we've been talking about. That means the electric field is basically the derivative of the potential. And so we can find the derivative of the potential. All that means the derivative is a difference, really. So if I want to find the electric field at any point in here, I know that the electric field always has to be perpendicular to the potential. I'll draw the electric field in a different color. I'll draw it in black. It always has to be perpendicular to the potential, and it goes from the area of high potential to the area of low potential. So it's going to look something like this at any point. It's always got to be perpendicular. Notice how I draw the arrow in the direction perpendicular to the equipotential lines, or it's an attempt to be there. This one could be a little bit better. They always have to be perpendicular. At the line of equipotential. Okay? So these are the electric field lines. They can look something like this. And then the value of the electric field, we usually take it to be kind of at the center of the difference between the two equipotential lines. We can find that by taking the derivative of them. What's the derivative? Well, it's this minus this divided by the distance between them. So here's your d, essentially. I'll call this one d1. I'll call this one d2. So if I know v3 and I know v2, divide that by the distance between them. That's going to give me the electric field strength at the point in between the lines of equipotential. And the direction, of course, is going to be perpendicular to the equipotential lines in a direction going downhill from the higher equipotential to the lower equipotential. So I'll call this the strength. And that's what you're going to need to know. That will conclude this video.